So before we go any further with sort of biologically specific metabolism, I want to step back a little bit and take a look at the enzyme kinetics that are going to be useful for thinking about metabolism. So this gets a little bit into rate constants, Michaelis-Menten kinetics, and things like that that are going to be useful in thinking about biochemistry, because really what we're concerned about in metabolism, other than mass action or substrate concentration, is the rate of the reaction, and that is really controlled by enzymes. It's a factor of covalent modification, allostery, negative feedback, things like that, but it's also a function of simply the inherent properties of the enzyme, and that's something that we're going to get from looking at this kinetics. So what I have here right now is an energy diagram of a certain reaction that's taking place. To orient you, I'm going to be using S for substrate, E for enzyme. This SE is the complex that forms when the enzyme and the substrate bind, and then P is going to be product. Okay, so on the y-axis here we have energy, and then on the x-axis is the reaction progress. This can also be considered delta T for change in time. Okay. So a basic concept that I hope we're all familiar with is that enzymes decrease the activation energy for any given reaction. That's their biological function, and they do so without being used up. So actually, what I should have here on the bottom is enzyme plus product, because the enzyme is still there. Okay, so you can see that without the enzyme, the activation energy that it will take in order for the substrate to go to product is this large amount right here. But if you add in enzyme, then that activation barrier decreases, and it's easier to get over this hump, right? And then another sort of concept that I just wanted to touch on while we had a reaction diagram up is this delta G. That's something that Nigel talked about in one of his first lectures, I think. That's a function of enthalpy, which is heat, and entropy, which we've already discussed a little bit. I think he said that you won't need to calculate any of those, but the important thing to remember is that delta G is an inherent sort of value in relation to the substrate and the product and the energy difference between the substrate and product, but it actually doesn't have anything to do with the enzyme. So you can see that if you are going through this reaction either with enzyme or without enzyme, it doesn't change the delta G of the reaction. That's an inherent function of substrate and product energy ratios. Okay. So if I were to write out this reaction in a sort of classical chemistry sense, then you would have the substrate and the enzyme that are separate entities. Okay. Let me put that a little bit lower so it's easier to see. So you have substrate plus enzyme, and then this can go either forwards or backwards, right? So that's that arrow notation that I was talking about earlier. Then you'll have the substrate enzyme complex after they've bound to each other, and then you'll go all the way to having substrate plus product, or sorry, enzyme plus product, because the enzyme doesn't get used up. Okay, so that's our basic reaction. You have substrate plus enzyme for this first step. This set of arrows represents this incline in the reaction diagram. Then this second set of arrows represents this drop. Okay. Something that I want to point out quickly is that not all reaction diagrams are going to look like this. So the products might not necessarily be a lower energy state than the reactant. So you could have something like this, where the substrate is in the middle here. You go over an activation hump, and actually product is up here. So it could be that the product contains more energy than the substrate. That's also a valid biochemical reaction. Someplace that might happen, just for your information, is when you're synthesizing glycogen, or when you're synthesizing fatty acids, those very energy-rich compounds. Okay. So if we go back to looking at this reaction diagram and this particular set of reactions, there are constants that are associated with these different steps. So you have to remember that each of these reactions is going forwards and backwards at the same time, and whether the reaction is going to go forward entirely depends on the rate of the forward reaction being larger than the rate of the reverse reaction. So I'm not going to go into how you derive these numbers, but essentially there are constants associated with these. So you have a rate constant for your forward reaction, that's Kf, and then the rate constant for your reverse reaction. Sorry, that should be on the other side. So Kf and Kr for forward and reverse. And then over this second reaction heading, you have Kcat, cat standing for catalysis, or this last bit of the reaction actually being catalyzed. Okay, so if you combine this Kf and Kr, what you're really doing is just looking at a ratio of K forward and K reverse. Okay, because as we said, whether the reaction is going forward or backwards is going to depend on the ratio, whether one of these is larger than the other. But from mathematics, if you combine one constant with another constant, you just get another constant. So we can simplify this. Bear with me, I know this is some math. You can simplify this ratio of constants into just a constant, another constant. And this one is called Km because we're talking about Michaelis-Menten kinetics. It's the Michaelis-Menten constant. So what do these constants actually represent? Well, if you think about substrate plus enzyme to substrate-enzyme complex, what's actually happening physically in this step? Whenever you're looking at chemistry or using mathematics in order to relate chemistry, biochemistry, and figure out what's happening, you always need to take a step back and remember that you're looking at a biological system, and have a little confidence in your own understanding of that. So between this first step and this second step, well, the substrate and enzyme are binding, okay? So this Km fundamentally represents the likelihood with which that will happen, okay? How strongly do substrate and enzyme bind each other? And then between the second and third parts of the reaction, what's happening here? Well, you're going from a substrate-enzyme complex to enzyme plus product. Okay, you're spitting out the final bit of that reaction. So what's physically happening? Well, the reaction is being catalyzed. So this Kcat represents a sort of speed of the reaction, or how likely that reaction is to be catalyzed. Okay. The reason I'm bringing this up is because if you go through a number of derivations that I'm not going to do because they're really boring and you don't need to know them, you can basically say that velocity, speed of the reaction, we say Vmax in kinetics because what you're really looking at, what you're interested in biochemistry is the maximal rate of any given reaction. Well, to sort of break that down, what all that really means is how much product are you getting over any given period of time. So this is change in product over change in time. It's a rate. How quickly are you generating product? That's what that expression means. Okay. So if you go through the Michaelis-Menten stuff, then you can simplify this, or you can write it in two different ways. You have concentration of substrate on the top, and then you have Km, this binding constant, binding coefficient, on the bottom, and substrate concentration. Again, don't worry about this bit, the substrate concentration. It's just some mathematics and putting it up here for your information. And if you want to relate all of this to the coefficient for catalyzing the reaction to go forward, it's Kcat times enzyme concentration, initial enzyme concentration, which really isn't going to change all that much in the biological reactions. And then you have this expression. Okay, so again, that's a lot of math. But if we look at what's fundamentally going on here, you can see that there is a relationship, okay, between Vmax, the rate of catalysis, and the binding coefficient. Okay, those are really the three bits that are important. If you put them in a mathematical relationship, changing kcat will affect Vmax, and changing km will also affect Vmax. What this essentially means is that if you increase kcat, which is from this complex of substrate and enzyme to enzyme plus product, you'll increase Vmax. Okay, and that makes sense because if the enzyme has this inherent property of being faster at catalyzing the reaction will go forward faster. Okay, that seems to make sense, right? Km is a little bit more complicated. So if you look at Km, you can see that it's on the bottom half of this ratio, and what that means is that it's actually inversely proportional to Vmax. So if you increase Km, you'll actually decrease Vmax. It takes a little bit of thinking to figure out why this might be the case, but you have to remember that Km is this binding ratio. Okay, how well does the enzyme bind its substrate to become this complex? Well, in a biological system, you actually don't want it to bind that well. If you think about the way that certain toxins work, say sarin gas, okay, what sarin gas does is it irreversibly binds enzyme, okay, the enzymes that are important for respiration and biological function. It binds enzymes better than the substrates bind their enzymes, and it binds so well that the enzyme will never ever ever release it as a substrate. If we consider sarin gas to be a substrate, it takes up the enzyme and then doesn't go through any reaction, and the enzyme never ever releases that sarin gas because it's bound so well. So actually, if you want to increase the rate of the reaction, then you should decrease how well the enzyme binds its substrate. It seems a little counterintuitive, but if you think about it, it actually makes sense. So what I'm going to be talking about in the next video is how this Km, which I'll be referring to in the future as binding efficacy, the binding coefficient, or affinity for an enzyme with its substrate or for a receptor with its ligand. We're going to be talking about how the Km can affect how receptors transport their ligands, their substrates, how enzymes associate with their substrates.